Atomic Physics, Lecture 1, The Structure of the Atom. Paragraph 1, First Ideas about the Structure of the Atom. Until the mid-19th century, the prevailing belief in science was that atoms are the smallest invisible particles of matter. In the late 19th century, evidence began to emerge indicating a complex atomic structure. For example, electrons were discovered, electrically charged particles emitted by atoms under certain conditions. As it turned out, electrons have a mass that is thousands of times less than the mass of atoms. It was found that atoms are complex systems formed by electrically charged particles. Paragraph 2. Thomson's atomic model. The first model of the atom was Thomson's model. W. Thomson, 1902, considered the atom as a homogeneous positively charged ball inside of which small negatively charged electrons are scattered throughout its volume. The electrons were assumed to be moving, oscillating around their equilibrium positions. In 1904, this model was developed by J. Thomson, who believed that the electrons inside the ball are located in the same plane and form concentric rings. For the motion of an electron in this model, an equation of harmonic oscillations is obtained. An electron performs a continuous harmonic oscillation with a certain frequency, and at this frequency, electromagnetic waves are emitted. The disadvantage of Thomson's model was, in particular, that it could not explain the line nature of the spectrum of the hydrogen atom, since it gave only one spectral line at a frequency equal to the electron vibration frequency. Paragraph 3. Planetary model of the atom. Thomson's model was replaced by the planetary model of the atom proposed by Rutherford in 1911. According to this model, at the center of the atom there is a massive positively charged nucleus around which electrons move. The movement of electrons around the nucleus is similar to the movement of planets around the sun. The collection of atomic electrons forms the electron shell of an atom. Thus, an atom consists of a nucleus and an electron shell around it. Initially, the disadvantage of the planetary model was that according to classical electrodynamics, a charge moving with acceleration in an electric field must continuously emit electromagnetic waves. Therefore, the electron would have to very quickly spend its energy on radiation and fall onto the nucleus. With the development of quantum mechanics, the planetary model was improved and this drawback was overcome. Paragraph 4. Quantum mechanical ideas about motion. The advent of quantum mechanics made significant changes in the understanding of the nature of electron motion in an atom. According to quantum mechanics, the movement of a particle cannot be considered as movement along a trajectory, that is, along a certain line in space, such as, for example, the orbits of planets. Therefore, the state of an electron in an atom can only be conditionally considered similar to the movement of a planet in its orbit. Unlike planets moving in orbits, the state of an electron in an atom is spoken of as moving in orbitals. Unlike a linear, one-dimensional collection of points that form an orbital is a spatially distributed collection of points. That is, it is a three-dimensional object. According to quantum mechanics, a particle cannot be considered as being at a strictly defined point in space at every movement of time. A quantum particle with different probabilities is simultaneously located at many points in space. Therefore, being in an atom, an electron does not pass through the orbital points one after another, but is located with some probabilities simultaneously at all points of the orbital. Thus, the electron does not move along a specific path. Paragraph 5. Blurring of orbital boundaries. An orbital does not have clear boundaries. The probability of finding an electron is maximum at the points forming the orbital and decreases with distance from it. Therefore, an orbital is defined as a set of points in space where the probability of finding an electron is especially high. However, we note that even at points not considered to belong to the orbital, the probability of finding an electron, although small, is non-zero. In particular, with some non-zero probability, the electron is even located inside the atomic nucleus. Due to the three-dimensional structure of the orbitals and the blurring of their boundaries, they are figuratively called electron clouds. Paragraph 6. Decrease in the density of orbitals as they move away from the nucleus. The further away an orbital is from the nucleus, the larger its size. Just as the farther a planet's orbit is from the sun, the longer it is. This means that the more smeared the location of the electron is, that is, the less likely it is to find the electron at each specific point of the orbital. This is similar to how the longer the planetary orbit, the less time on average the planet spends at each point. Figuratively, we can say that electron clouds, as they move away from the nucleus, become, on average, more and more rarefied. Paragraph 7. Set of orbitals. The electron shell of an atom is a set of orbitals in which electrons are located. Note that all atomic orbitals are different. They differ in distance from the nucleus, size, shape, and spatial orientation. Since the electron is a quantum object, the parameters that characterize its various orbitals represent a discrete set of values. Consequently, the orbitals form a discrete collection. In particular, the average distance at which the orbital is located from the nucleus can only have certain discrete values. Thus, an electron in an atom may not be located at any distance from the nucleus, but there is a discrete set of allowed distances. Moreover, these permissible distances are different for atoms of different chemical elements. Paragraph 8. Energy levels. The energy values that an atomic electron can have, as well as the spatial characteristics of the orbitals, form a discrete set. Thus, the energy of an electron in an atom cannot take any value from a continuous series, but there is a discrete series of permissible values. These acceptable values are called electron energy levels. The remaining energy values are forbidden for the atomic electron. At the same time, atoms of different chemical elements have different ranges of permissible energy values. That is, the atoms of each chemical element have their own set of energy levels. In general, different orbitals correspond to different energies of the electrons located on them. The closer the orbital is to the nucleus, the lower the energy it corresponds to. However, degeneracy of energy levels can occur when an electron in different orbitals has the same energy. Paragraph 9. Pauli's exclusion principle. Different electrons in an atom occupy different orbitals. This is due to the quantum mechanical Pauli exclusion principle, which is valid for particles with half-integer spin. According to this principle, two particles cannot be in the same state. This means that two particles with the same other parameters cannot occupy the same region of space. For an atomic electron, these other parameters are energy and spin. This means that two electrons with the same energies and spins cannot be in the same orbital. Each orbital corresponds to only one energy value of the electron located in it. The spin of all electrons is also the same, a half in units of Planck's constant. However, since spin is a vector, the state of the electron depends not only on the magnitude of the spin, but also on the direction. According to quantum mechanics, a spin equal to a half can only have two opposite directions. This means that each orbital corresponds to two different states of the electron, differing in the directions of their spins. This means that each orbital that contain no more than two electrons with oppositely directed spins. Therefore, in multi-electron atoms, all electrons are not able to fit into the one orbital and are forced to occupy many different orbitals. Paragraph 10. Ground and excited states of the atom. Electrons fill free atomic orbitals not randomly, but in order of increasing their energy. That is, the orbitals closest to the nucleus, which correspond to lower energy, are filled first. An atom in which all orbitals are sequentially filled, starting from the lowest energy to their corresponding maximum energy for a given chemical element, is in the ground state. The energy of an atom in this state is minimal. An atom can remain in this state for any length of time. An atom that has gaps in the order of filling its orbitals, that is, orbitals with lower energy turn out to be empty, is in the excited state. In this excited state, the atom has excess energy. Each atom has many different excited states depending on which orbitals are empty and which are occupied. Since any physical system strives for a minimum of energy, an atom is usually in an excited state for only a very short time. Its electrons are quickly redistributed between orbitals to occupy empty spaces with lower energy. In this case, the energy of the atom decreases and excess energy is carried away from the atom in the form of electromagnetic radiation.